So we've already talked about how the derivative is the same thing as the slope of the tangent line, which is so the slope at one point, the derivative, and the instantaneous rate of change. So these are all equivalent. So anytime you see any one of these things, you want to think, I want the derivative, right? We talked about finding the derivative or the instantaneous rate of change the really long way with the limit definition of the derivative, and then we learned some shortcuts yesterday, right? So from here on out, we'll be learning lots of shortcuts, but we're going to talk a little bit today about the meaning a little bit more on a graph. So we're going to find the derivative on this graph for each of these values. So when you're thinking graphically, we want to focus on slope of the tangent line, right? So let's go ahead and estimate the derivative. So here we're going to estimate f prime of -7. And we're estimating because we don't know what the actual function for f is, so we can't calculate the derivative, right? And so we're going to just estimate it by using the graph. So x is -7 at this point right here. So if we were to estimate the derivative, we would need to estimate the slope of the tangent line at that point, right? So we're going to draw our tangent line, so a line that goes through just that point and just touches the function at just that point. So that would be a good estimate of the tangent line. Can you guys see that okay? And then we want to estimate the slope of that line. So like here, if we go up 1, 2, 3, and then over 1, it looks like that probably has a slope of 3, right? Because if you go over 1, down 3, that looks pretty darn close. So it looks like the slope of this tangent line is probably about 3. Depending on how much you drew it slanted, maybe it is a little bit closer to 4, right? Or 3.5, that's fine, right? We're estimating here, okay? So then let's go ahead and do that for each one of these. So if we do f prime of -6, go ahead and draw that tangent line at -6. So this is -6 right here. Draw what you think that tangent line would look like. This one's going to be a little bit less steep, right, than the one we just had in order to just go through that function at one point. It'll be a little less steep. And then if we estimate the slope of that, it looks like a little bit more like 2, I think, right? Because if you go up 2 over 1, you're going to run into the slope of that. So I think 2 is a good approximation. Again, depending on how perfectly you drew that tangent line, it might be off a little bit. And then f prime of -4 will be the slope of the tangent line at -4. So this is -4 right here. That will be the point there. So what is that? That one's easy. What's that tangent line slope going to be? 0, right? If your tangent up at the tippy top like that, your slope will be 0. So that's probably pretty darn accurate. And then the next one is at -2. So that's this one. That's what a tangent line would look like at that point. That slope looks, now we're at a negative slope right now though, right? But it looks like it's about 1 over 1 up 1. But now we're at a negative slope. So it'll be about -1. And then at -1, this is a little interesting because your tangent line might feel a little funky. It's going to be right along here. Kind of when you're close by, it's going to look like it's going to be right along the curve. This is also negative, a little bit steeper. Looks like about -2 down 2 over 1. So it's a little bit steeper than the last one. At 1, we'll be down here, so we'll have a horizontal tangent again, so our derivative will be about 0. Should be pretty accurate. And then at 3, we're about right here. That's pretty steep. It looks like 3, maybe down 3 over 1. We're positive again now, though. Our derivative is positive. Up here again at 5, when x is 5, we have a 0 slope again. And then over here at 7, we're back to a negative slope. Maybe like a -4. That's pretty steep. Depending on how steep you drew it. Maybe you had a little bit steeper or less steep. If you said -3 again, that's fine. But mainly we want to look at the idea that the tangent line to the curve, right? The slope of that is your derivative. So here, with these points over here, our slope was positive, then we were 0, then our slope was negative during all of these, right? All of these tangent line slopes are negative. And then over here, our tangent line slopes were positive again, and then they went to 0, and then they became negative again. So what I'd like you to do is let's think about whether the function is increasing, decreasing, or has like a relative max or min at each of these points, okay? Because this is going to tie into what we're going to do next. So at this point right here, what is my function doing? Is it increasing or decreasing? It's increasing, right? It's increasing from here to all the way up. So at both of these two, it's increasing. What do we have when the derivative is 0? We have a relative max there at -4. Then when all of these slopes are negative, what is my function doing during this time? For all these negative slopes? It's decreasing, right, during this time? And then at 0, at 1, the derivative is 0, we have a relative min. After that, this value over here, when we went positive again, it's back to increasing. It's 0 again at the relative max up there. And then when it goes back to negative slope, we're decreasing now. So based on kind of what we see here, right, it seems like when my derivative is positive, what does it look like my function is doing when my derivative is positive? Increasing. It looks like when my derivative is greater than 0, that f is increasing. When my derivative is less than 0, it looks like f is decreasing. And then wherever we have relative maxes and mins, my derivative is what? 0. So right now, these are just observations, but they're good observations. And we'll kind of see if this holds true in another example here in a minute. So on the next page here, we're going to look at estimating the derivative at from a table of values. Okay, so if we have a table of values, how can we estimate the derivative? So let's come down here to the next page. And we're going to estimate the derivative from a table of values. So when we don't have a graph, but we have a table of values and we know function values, okay, we can approximate the instantaneous rate of change with the average rate of change, right? That's how we even got to the instantaneous rate of change in the first place. So if we don't know the derivative at a point, we can do that by picking 2 points around it and finding the slope between those 2 points. And that will be a good approximation nearby. We want to be the closest that we can, so you want to pick the closest interval containing that point, because you could pick a lot of intervals that have that point in it, but you want the closest one. So for example here, if I want to find f prime of 0, I don't know the derivative here. I just know some particular function values. But if I choose the interval -3 to 1, that will be the smallest interval containing 0, right? Without 0 being one of the endpoints. Okay, so that'll be the smallest interval containing 0 without 0 being one of the endpoints. So if I can find the slope between those 2 points, that will be the average rate of change, and that will be a good approximation of the instantaneous rate of change. At least it's not great, but it's better than anything else we've got. So then we'll do the slope. So we'll do f of -3 minus f of 1 all over -3 minus 1, change in y over change in x. Or you can do it backwards. That's fine. So f of -3 is going to be 2. F of 1 is -3. No, minus -3, so +3. And then that'll be -4 in the bottom. So we'll have -5 over 4. So again, this is an approximation, so we probably should use approximation symbol right here. So this isn't the perfect derivative or the perfect slope of the tangent line, but you can at least see that it's negative, right? And it's bigger than 1, probably. Okay, so that could tell us some important information. So for B here, if we want to find f prime at 1, we could pick an interval containing 1, so the closest one will be 0 to 4 with the values that we're given here. So we can do f of 4 minus f of 0 over 4 minus 0. So that'll be 0 minus 1 over 4 minus 0. So that'll be -1/4. So again, we can see the derivative is negative at this point as well. So maybe with what we've been talking about, we could maybe decide that this is possibly decreasing at this point, right? If that holds true. If we want to find an approximation for f prime of 4, we could pick 1 to 6 because that's the closest interval containing 4. So f of 6 minus f of 1 all over 6 minus 1 will be your average rate of change. So it'll be -7 plus 3 over 6 minus 1. So it'll be -4 over 5. So now our rate of change is less than 1, but it's still negative. And then to approximate f prime of 6, we could pick 4 to 10. So 2 minus 0 over 10 minus 4. And that'll be 1/3. So now it's positive. Now we've got a positive slope. So we probably switch to increasing at some point there. Okay, so now let's look at another graph and kind of see if our intuition is correct, okay? So first let's look for wherever our derivative is negative. So wherever our slopes will be negative. So to do that, you can kind of imagine holding a pencil up and a tangent to the curve and kind of imagine when it will be negative. You could draw some tangent lines here, right? And so this first part here, is my slope positive or negative? Is my derivative positive or negative? Positive, so that will be from -∞ to -4. That my derivative, I put that in the wrong category. That's the negative category. Positive is down here. negative infinity to negative 4. And then at negative 4 itself, my slope would be what? 0. So at negative 4, the derivative will be 0. Then on this side of negative 4, my tangent line slopes all would be what? All of these guys are going to be negative. So we're negative from negative 4 to negative 2. It's 0 again when we hit this little valley, right? So at negative 2, the slope, i.e. the derivative, slope of the tangent line, i.e. the derivative. Then my slopes start getting positive again if I draw little tangent lines here from negative 2 to 1. Zero again up here at the peak, so at x equals 1. And then negative all of these times on the other side, so from 1 to infinity. So we talked about derivative being positive, seeming like it was increasing, derivative being negative, seeming like it's decreasing, and then at the mins and maxes having a derivative of 0. Does that seem to hold up with this graph as well? All right, all of these times it's increasing, then decreasing, then increasing, then decreasing, and we have a derivative of 0 when we have relative max and min, which also makes sense, right? Because the derivative is also the rate of change. So if the rate of change is positive, then that means that the function is going up, right? If the rate of change is negative, then that means the function is going down. And this is official. So on the next page, I have a nice little official summary of what we just said. This is true. This is official. Okay. If f prime is positive, then on an open interval, then we could say it's increasing all the way up until the endpoints. If f prime is negative on an open interval, then it's decreasing all the way up until the endpoints. And if the derivative is constant on an interval, then it would, or is 0, then it would be constant. We haven't seen that example, but that's also something we can look at. So let's go ahead and look at this example here to try to officially explain what's going on here. This one's different though because our graph here is h prime of x. This is the derivative graph. So this is not h of x itself. This is the graph of the derivative. So if we don't have the graph of h, right, but we do have the graph of the derivative, when did we say the h would be increasing? When the derivative was what? Opposite. Derivative positive. Yeah. So for increasing, that would happen when h prime is positive. If this is the graph of h prime, can we figure out when h prime will be positive? Yeah, we can see, right? It's positive all the way during this time, right? It's above the x-axis, and during all of this time. H prime is positive during all of that. So h prime is greater than 0 from negative 2 to 1 and 3 to infinity. So that tells us that h of x is increasing. And it says to give a reason for your responses, i.e. a justification, right? So this means to justify. Well, we don't need a lot of words to justify this. What we wrote down right here, the h prime of x being greater than 0, that's a justification, right? Because that's now a fact, right? That when the derivative is positive, it's increasing. And in fact, we can make all of these intervals closed brackets, except for the infinity. Because it says if it's increasing, or if the derivative is positive from negative 2 to 1, then it's increasing, including the endpoints. And so then we could also look at where h is decreasing by looking where h prime is negative. And so if we look at where it's below the x-axis, that will be these times right here. So from negative infinity to negative 2, and we'll go ahead and include the endpoint because if it's negative up until negative 2, then it's decreasing until negative 2. You get to include the endpoint. And then from 1 to 3. And then the last thing that we addressed is we said, well, when the derivative is 0, it seems to be that we have relative maxes and mins. So the derivative is 0 at 3 points here. These 3 points right here, the derivative is 0. But we can actually figure out whether it's specifically a maximum, or we can figure out whether it's a minimum if we know what happens to the derivative, right? Because if the derivative is negative during, like, we'll look right here on this side. The derivative is negative right before negative 2, right? What does that mean if the derivative is negative? What is the function doing? Increasing or decreasing? Decreasing, right? So if the derivative is negative, then that means h of x is decreasing, right? Before negative 2. H of x will be decreasing, right? And then after negative 2, my function switches to increasing because the derivative switches to positive. So then it would switch to positive. And when our function goes from decreasing to increasing, do we have a minimum or do we have a maximum? When it goes down and then up, we have a minimum. So if it's decreasing to increasing, right, it's going to go down then up, we're going to have a minimum. So if the derivative changes from negative to positive, we're going to have a minimum. So we can see that right here. If f prime changes from negative to positive, then we have a minimum because we will be changing from decreasing to increasing, right? Whereas if f prime changes from positive to negative, that's going to be a maximum because that means f is going to be going from increasing to decreasing, right? And give you a maximum. So at negative 2, the derivative goes negative to positive. The derivative is negative before negative 2, and it's positive after negative 2. So that will be decreasing to increasing. So that will be a relative minimum. So we can say there's a relative minimum at x equals negative 2. And is there any other zeros where there's also the change from negative to positive? Specifically in that order, out of those 3? This one right here, it goes negative to positive, right? So this will also be a minimum. So at 3, we're also going to have a minimum because the graph goes from negative to positive. And then we do need to justify our answer. So we would say because f prime changes from negative to positive. But at x equals 1, when the derivative is 0, the graph goes from positive to negative. So the derivative goes from positive to negative. So your function will go from increasing to decreasing, which will give you a maximum. So that will be a maximum because f prime changes from positive to negative. So not only is the derivative 0 at these relative mins and maxes, but how the derivative changes tells us about whether you have a min or a max specifically. Okay? And these are what justifications would look like for those.